But again, welcome back to ME 760 Engineering Analysis 1. So last time we finished chapter number 11, and we will start now chapter number 12, which is the line and surface and volume integral. So let's start. So this is chapter number 12. And it is line, surface, and volume integrals. So usually before starting the chapter, usually we will see that sometimes you have line integrals, and those line integrals can be convoluted or converted into double or surface integral. Double or surface integral. And vice versa. This usually, if you have a force integrated over a line, for example, so this is line integral over a contour. So it is, you can transform it to the same integration of the force or the function f over certain area. So in this case, this will be an area A. So this is called the Gauss theorem. Gauss theorem. And sometimes you will have, of course we will come later during this chapter on how to derive this maybe. So sometimes you will have triple integrals. And you can convert to surface integral and vice versa also. Can you give me an example? Can somebody give me an example of converting a volume integral to a surface integral?
To do it for conservation of mass.
Yeah, but it's the Green theorem, and it is what? If you have a volume integral of f dv over a volume, this is equal to what? FDA. And this is divergence of this over the volume, divergence of the force. And this is, by the way, here, this is just curl of f over a line integral equal to f dot dA. And this is divergence of f over the volume V is equal to f dot dA. So this is just two theorems that we'll study during this chapter to show you how to transform from line integral to a surface integral and vice versa, or from volume integral to surface integral and vice versa. So now let's start by looking at the line line integral of a vector function. So let's assume that we have a curve C. This curve is C, and I have a position vector here pointing up to R from origin O. So let's assume that we have a curve C, and this curve C is given parametrically by R as a function of the parameter U, and it has three components: xu in the I direction plus yu in the j direction plus zu in the k direction. So if this curve is smooth, this curve is smooth. So what do we mean by smooth curve? Smooth function. What do we mean by a smooth function?
It's continuous and differentiable.
Yeah, continuous and differentiable. So you don't have discontinuity, whether it is finite or infinite, for example. So you don't have something like this. A curve, then you have this curve like this. So this is finite discontinuity. What does it mean? That at this point you have a finite discontinuity. Can you give an example of infinite discontinuity? What function usually we have that shows infinite discontinuity? Lots of function in mathematics. Logarithm. So logarithm at x equal to what? 0, it goes to what? Infinity. And what else? Trigonometric? Yes, the tangent. Yes? And so on. So those are infinite discontinuity. And also 1 over x. When x equal to 0, it goes to what? Infinity. So 1 over x. Okay, guys? So if the curve is smooth, and by smooth, by definition of smooth curve, we define it as if it has a unique tangent, at every point. At every point, and that varies continuously with you. So we can integrate the line integral of a function f as a function of r if we want to integrate a function f of r over dr in line integral, for example, on a contour C. So we have this curve C, and we want to be able to integrate a function over this curve. So this is f of r dr. We want to integrate it over the curve C. Let's assume we will integrate from A to B, from point A to point B. Let's assume that here is A and here is B. So u equal to A to u equal to B, for example. So from A to B, the function is a function of r, and I can dot this with dr, but r, the curve, is a parametric in what? In u. So I have to do what? The chain rule. So this will be dr by d what? Multiplied by du here. So this will give you what? This will give you dr, if you cancel both. This will give you dr. But what's f of r multiplied by dr by du? What's dr by du? From here, dr by du is just equal to what? X prime of u in the I direction plus y prime of u in the j direction plus d prime of u in the k direction. Yes, guys? And this is dr by du. So if you dot this with f of r, let's assume that f of r has components f1 in the I direction plus f2 in the j direction plus f3 in the k direction. So when you do the dot product, this multiplied by this, what will be? F1 x1 prime, f2 y prime, and f3 z prime. Yes, guys? So this would be from A to B, f1 x prime plus f2 y prime plus f3 multiplied by z prime, all integrated over delta u. Sometimes the integration over a contour, like a curve like C, if the C is, let's say, if the C is closed like this, and this is C, sometimes you write it like this or you write it like this. So this is, you are integrating over the contour C, or this is a closed integration over a contour. So this is just the results of the line integration for a vector function over a contour like this. So let's take an example. So in this example, let's assume that I have two functions or two curves. So this is x, y, and z. And then let's assume that point A, the start of the curve, is here, and point B, the ending of the curve, is here. So this is the start and this is the end. So the start is point 0, 0, 0, and the ending point B is 1, 1, 1. So you have one here, and one here. Okay, guys? So, and I have two curves, C1 and C2, that connects between the beginning point and the end point. We are just taking an example. So if the vector function that we want to integrate it over those two separate contours, f as 3y in the I direction plus xyz in the j direction plus x square y in the k direction. And now let's look for the two curves that we want to utilize, and we want to integrate the function f over. So the curve, the first curve, is just a line. So C1 is just a line, and the equation of this line is just R1 as a function of u equal to u in the I direction plus u in the j direction plus u in the k direction. So u should be, in this case, what? 1, 1, 1. Yes. So if you have one in the I, one in the j, and one in the k, you will reach this point. So this is just a straight line. So let's look at the contour C2 And this is just equation for this contour is u in the ith direction plus u in the jth direction plus u cube in the kth direction. So this curve, you go one in the x direction, one in the y direction, but in the z direction you go like u cube. So you have this curve. Okay guys? So this is two separate curves and we want to integrate the function on these two curves. So now let's look at the function f over the contour C1. The function f is just what? 3y in the I plus xy z in the j plus x square y in the k direction. So we want to know how this function will look in each direction of those two curves. So f1 3y. Yes? What's the components of the first contour? X equal to what? U and y? U and z? U. So in this case, I will substitute y equal to what? U. So this will be what? 3u in the I direction plus xyz will give me what? U multiplied by u is what? U cubed in the jth direction plus in the k direction it will be what? U cube again in the k direction. So let's look at the function, same function in the direction of the contour C2. Can you tell me in the C2 x is what? U. Y is what? Z is what? U cube. So this would be what? 3 what? Plus xyz u fifth in the direction of j plus u cube in the direction of k. Did you get it? Okay. So now let's do the first integration of f of r dr over C1. So again, we can replace f dot dr by what? By f dot dr prime du. Yes? Which is this one. This one is what? R prime. Yes guys? So it will be f dot dr prime integrated over du. This is what? A scalar or a vector? A scalar quantity. And this is the scalar quantity. Yes guys? So now this will give me what? So I want to integrate over the curve. So I will integrate from u equal to what? Yeah, but what's a? At this value u is equal to what? 0. And at this value u is equal to what? 1, because 1, 1, 1, you will get to the point what? 1, 1, 1. And if you put u here equal to 1, 1, 1, 1 cube will give you 1, you will reach the same point. Yes? So I will integrate from 0 to what? 0 to 1. So the first curve f of u is what? 3u in the I direction plus u cube in the jth direction plus u cube in the kth direction, dotted with what's r prime from here? 1 in the I direction plus excuse me plus what in the j direction? Plus 1 in the k direction. So it will be ijk integrated over delta u. Do you have any questions so far? So now, do the dot products here. So this would be what? 3u. From 0 to 1, this will be what? 3u plus 3u cube plus what? u cube du. This is what? 2u cube. This will give you what? 3u, what's the integration? And what's the integration of this one? 2/4 y to the power of 4. So if you do this at 1, this will give you what? 3/2 plus 1/2. And at 0, this will give you what? 0. So what's this? 2. So now let's integrate over C2. Excuse me. This will give you what? What's the F over C2? 3u plus u to the power of 5 in the jth direction plus u cube in the kth direction, and this is I plus j plus k. This will give you what?
Wouldn't C2 be,
What do you say?
would C2 for dr prime be, have 3u squared?
Yes, I'm sorry. 3u square k. You are right. So what will be the multiplication now? So it will be 3u plus u to the power of 5 plus 3 to the u power of 5 du. This is what? 4. So this, what will be the integration then? 3/2 u square plus, this will be what? 4/6 what? From 0 to 1, 0 will cancel, and 1, this will give you what? 3/2 plus what? 4/6, and this will give you what? 13/6. So what we got from this example? That going from point A to B depends on the contour. Yes? It's not only the contour, but as note here, the integration from A to B over curve C depends on the shape of the function, or the function f, and it will depend on what? The end points A and B, and also it will depend on what? The curve C. Yes, guys? So whenever you integrate from initial point A to final point B, the integration for the vector function over this curve will depend on 3 things. The first thing is what function are you integrating? The second thing is what? The endpoints A and B. And the third function is what? The path that you are taking. So technically speaking, we will say it depends on the path. Okay? So what's the common application for this line integral? A common application is the work function, or the work. And what is the work? to integrate what? The force dotted with R over certain. So if you have a force, if you have a particle here moving from point A to point B, and this is particle, and the particle will have a position vector, this is origin, and it has a position vector R. Let's assume that it's R of t, and there is a force that tries to pull this particle from point A to point B. Then what you are doing is you are dotting F dot dr, and dr usually will be in what direction? Tangent to what? Tangent to the curve. So this is an angle theta, so this will be what? The work is just F dr cosine theta. So whenever you are perpendicular to, if the force is perpendicular to dr, what will happen? The work is what? Zero. And this is very obvious when you have a magnetic field. The force of the magnetic field is equal to what? Q V cross what? V cross B. V is the velocity and B is the magnetic field. So if the magnetic field is in the Z direction and the velocity, let's assume the particle, when the particle will rotate in the XY direction. So this is X, Y, and this is Z direction. So the velocity will be like this. So this is the velocity vector, the velocity here. This is the velocity. So V is in what direction? XY, and this is in what direction? Z direction. The force will be in what direction? So this is, let's say that XY in this case will be, if we take cylindrical geometry, this is theta. So F, it will be in what direction? In R direction. So the force will be, always the force will be what? In this direction. Of course it will be negative R. It will pull the, try to pull the particle to the center. And there is a centrifugal force that try to pull the particle outside. So there is a balance. So does this force make a work or not? So where is the force now? Let's look at it like this. So the velocity is in this direction, and delta S will be in what direction? Or delta R will be in what direction? That direction. And where is the direction of the force? Here. Yes? So F dot dr is equal to what? Equal to the force. This is the force. And dr is in what direction? Yes? What's the angle between? 90 degree, because the tangent to the circle is perpendicular to the radius. Yes? So this is equal to what? So the work for the magnetic field is always equal to 0. This is why we said the magnetic field does not accelerate particles. Not accelerate, does not have energy, does not give energy, because acceleration is a vector. It accelerates particles. Why?
Because it's moving in a circle.
But because of what? Because the velocity is a vector, and although the amplitude of the velocity does not change, but the direction of the velocity what? Do change. So the direction of the velocity do change. So there is acceleration in the sense that your vector always what? Always changing. Yes? But what's the energy giving to the particle? 0. Because the energy is just what? V dot V. Okay? Of course, the amplitude of this divided by 2 multiplied by m. This is the energy. Okay, guys? And if you look at V and you dot V with V, you will notice that this is equal to 0. Okay, guys? So the work given to the particle is what? Is 0. So this is one of the applications for the line integral and so on. So when the path integral will be independent of path. So the path integral, we saw here that it's not independent of the path. So only the path integral will be independent of the path if the function f can be represented as a gradient of a scalar function f of r. This is a vector function, this is a scalar function. So if we can get 2 points here, A and B, and we have a path like this, another path like this, another path like this. So the integration from A to B for f of r dotted with dr will be path independent when f can be represented as a gradient of another scalar function f. So let's look at the proof. R prime of u, we just wrote R prime of u, it's what? Let's look at R first. So this is x of u multiplied by what? In the direction of I plus y of u in the direction of j plus z of u in the direction of k. Okay, guys? What's f dot dr? F dot dr from A to B, let's say from A to B or from over C. This will be what? So I will say that this is divergence gradient of f dot dr over C. And what's this? What's the gradient? df by what? dx in the I plus df by dy in the j plus df by dz in the k dotted with what? X in the I plus y in the j plus z in the k. And there is dr here. Is it dr? No, this is like this. Du. And this is prime, prime, prime. So I will replace f dot dr is equal to what? F dot dr prime multiplied by delta u. Yes? This is the one over there. So now, if you evaluate the dot product, what this will be? So the integration now is from point A to point B. If you integrate it, this will give you df by what? By dx multiplied by what? By x prime, which is what? Dx by d what? By du plus df by what? By dy multiplied by dy by du plus df by what? dz multiplied by what? dz by du, all integrated over du. What's this, guys? Huh? d what? So this is the total differential df du. Yes? And integrated over du. This is equal to what? So this is the total differential for the function f. Yes? So if you have df, what's the integration of df? F from what? A to b. So this will give you what? Does it have any dependence on the contour that we are integrating over? No. So just to give us what? Huh? Functional dependence that just depends on the initial and final points, A and B. So we said that if we have a function, yes, if we have a function that can be represented as a gradient of a scalar function, a vector function that can be represented as a gradient of a scalar function, the path will be path independent. The integration over the contour will be path independent. Conversely, we can say that if we have integration of f of r dr, and this integration over a contour C, and this integration is path independent. This integration is path independent. I can say that the function f is what? Can be represented as what? Gradient of what? Scalar function. And what do you think? What a function can be represented? Can somebody give me an example of this? What about gravity?
Constant force.
What's the force? Equal to what? M1, M2 multiplied by what? G over R square, and this is in what direction? Direction of R. But we knew that the force is a gradient of what? Negative gradient of what? A function V is called the potential. Yes? What's the potential? Potential. So it's the potential. This potential is just, if you will do, let's say that this is what's gradient? D by dr of what? Of V. So what's V? F what? From here, negative F the dr. Just dV equal to F dot dr. Yes, guys? So what's the force? Negative. What's the force? M1, M2 multiplied by the gravitational constant divided by what? R square. Yes? Dot dr. Here is dr. Yes, guys? Okay? So now let's assume at r equal to 0, the potential is, let's say we will call the potential 0. At an r equal to r, the potential is what? Let's assume that potential at r equal to infinity is 0, and at point r is V of r. So what's the integration of this? V of r. What V of r will be? This is equal to what? M1 is constant, M2 is constant, G is constant. And what's the integration? This will come upstairs, it will be r to the power of what? Minus 2. So you will add 1. It will be r to the power of minus 1. So this will be over what? Over r. And you have a minus sign. Yes? Minus sign will cancel minus what? Sign. Then you will integrate from what? R to infinity. At r, this is equal to what? R, substitute R. And at infinity, this is equal to what? 0. So you will have what? So this is the gravitational what? Potential of the Earth. Yes? This is the gravitational potential of the Earth. Of course, if you want to get the gravity, so let's assume that m is the mass of the Earth. So instead of m1 and m2, m will be the mass of the what? Mass of the Earth. Mass of what? Mass of the Earth. So what's the force? Small m multiplied by capital M G over R what? R square in the direction of R. What's this? This is what? Force equal to mass multiplied by what? Acceleration. What's the acceleration and the gravitational field? G. Okay, guys? So this is the acceleration. And what's this? What's this? For the Earth. Yeah, but this is not this is what? This is the gravitational potential of the Earth. Gravitational potential of the Earth. Yes? So this is why when we want to calculate what's the gravitational potential for somebody, you are standing here, this is the ground, and there is a guy on the ground, another guy on a building, skyscraper, which is h high. What's the gravity here is zero. The gravitational, let's say, gravitational potential here is zero. This guy's, what's the potential energy of this guy? mg multiplied by what? Multiplied by h. M multiplied by g. Yes? And what's h? H is some r from the radius of the surface of the Earth. Yes? So this would be what? M multiplied by g multiplied by h. So r will go as r square, and it will give you what? mg over r multiplied by m is the potential. Yes, guys? So now I can represent the potential, the force of the Earth, the gravitational force, as a gradient of a potential. So if you just get from A to B for the force dot dr, this will be gravitational force, can be represented as negative grad V dotted with dr. And if you do this, this grad V is what? Where is grad V? Yes, it is. Yes? So V is just equal to what? mg divided by r. Yes, guys? What's grad V? Negative mg over r square multiplied by r in the direction of r. Yes? So if you just dot those two, this will give you mg over r square in the direction of r dotted with dr. If you will do this between A and B, you will notice that this is just the potential at A minus the potential at B. So, and this is very obvious. When I asked you, a guy was, this is ground, and this is 10th floor, and this is 100th floor. A guy take the elevator from the 10th floor to the 100th floor. So I asked you, what's the potential difference between those 2 points? It will be what? The potential at what? At hundreds minus the potential at what? does not depend on did you go and climb the building, does not depend on did you take the elevator from inside that goes you from here to here, or somebody drag you with a rope, big rope, and bring you like here, or you got a helicopter that took you from here, then go from here, and from here, and then come back to you to here. Does not depend. So those types of function or fields that going from point A to point B in this field does not depend on the path, it's called conservative fields. So those are conservative fields. So next time I'll stop here. Next time we'll take a couple of examples maybe and continue. Do you have any questions? Okay, thank you so much.